Right, sorry for the slight glitch. Good morning. Obviously, not obviously, but I'm actually honored to be able to address you here on this occasion. Probably shouldn't shout so much. At the same time, I feel a bit in a quandary because I'm supposed to give the quantum talk to an audience that I imagine to be extremely mixed and of all sorts of different expectations. Obviously, when talking about quantum information science, there is a great temptation on everybody's side, especially on the specialist side, to talk a lot about quantum computing. Quantum computers are in the news all the time nowadays. I've seen Google has just announced an upgrade by the end of the year to their superconducting device with 49 qubits predicted. D-Wave is producing upgrades to their so-called machine on a pace similar to Moore's law. We have quantum communication, quantum cryptography, quantum metrology, and all of those fields, they generate a lot of attention and press, obviously. So it's kind of easy usually to give one of those droning talks where you just show lots of pictures, and I'm not very good at that, unfortunately, but I have colleagues whom you should have invited who can do that very well. Sorry, I had this technical problem. It threw me off my little plan. Sorry, I'm gone. Anyway, sorry. So I take it for granted that you have heard about all of those things, that you know that there is a lot of technical promise and so on in quantum information science. And besides, I don't want to just go and bedazzle you by simply putting a quantum in front of every word that I say, which is also easy and very common. I mean, probably I've done that anyway in this talk. The truth is, quantum information theory, quantum information science has a problem, or quantum theory has a problem, and the problem is it's kind of too mysterious. So when we talk about it, when we talk about it, everything turns out to be, or when we try to reason about it in ordinary terms, which is common in presentations like this one, we tend to say things that are either wrong or sound like paradoxes or completely ridiculous. And so we are left behind some kind of smoke screen, and everybody is supposed to just believe me because I'm the expert. So that is why I want to confront the mystery or the problems that we have in understanding quantum mechanics. This is, by the way, from a play by George Bernard Shaw. So he understood this problem of quantum theory and its public perception already a long time ago. There is an entire wiki page only on quotes about quantum mechanics. I don't think there's any physical theory that has such an echo in popular culture as quantum theory. And one of the reasons is that it produces all these kind of weird effects. The specialists say crazy things. And yeah, the truth is that even the specialists, they don't understand very well what's going on. I mean, there are wonderful statements by Feynman. And this one here I took from a book by Ben Schumacher. Actually, like the previous quote, it's not on the famous website, on the wiki page. So by the way, this guy here, this is Ben Schumacher. This is him explaining the qubit, which is the term that he invented. It's one of the biggest gifts to the theory I'm working on. So this is also one of those statements that are wonderfully poetic and quotable. They don't mean anything if you haven't thought about quantum mechanics. Rather, maybe they resonate with some things that you've heard from philosophy and so on. But it does actually say something very deep and at least partially true about quantum mechanics. So yeah, so today I just want to do something very simple. I don't want to talk about quantum technology very much. And I want to focus on one of the most basic things in quantum mechanics, which turns out to be pure information theory, which is how do we get information about quantum systems. And so I drew these little cartoons. I will have more of these cartoons, and I'm sure you like them because they, like the way I drew them, they are already communication diagrams. There are agents, there's a flow of something. But okay, let's focus on the right-hand side. So these two famous scientists, they want to learn about this quantum system. So quantum system, okay, that's this weird microscopic thing. It's described by a wave function. So I drew this wavy line, and we give it a name psi. And so the peculiarity of quantum mechanics is that we do not actually see the wave function. It's not like any other physical theory that somehow comes with a silent assumption that the necessary parameters are in principle dynamical parameters. Instead, we have to make a measurement. It involves a choice. We have to make a measurement, choose a measurement. That means looking, and then observe the outcome. And the other peculiarity of the theory is the outcomes are stochastic. So every problem in quantum theory, and in particular every problem in quantum information, is a statistical inference problem. So to make this a bit more concrete, to go into a mathematical model, what we want to learn about is not just the wave function or something. We want to learn some property of the system. So there are actually different possible wave functions prepared by some agent. This can be people, but it can be also a natural process, obviously. And so this kind of setting, where X runs through some set of either messages or natural properties, that includes a lot of things that we do in both ordinary statistical inference, and particularly quantum statistical inference, like tomography, metrology, property testing, etc. And of course also communication. I hope that everybody, I mean, I mentioned popular culture before, right? So we were all reading Wikipedia and so on. So I hope you recognize all four of those people. If you don't, then you ask a neighbor. Okay, for the rest of the talk, I will mostly focus on the simplest case of only two hypotheses. Because obviously that's the most primitive one, and we can learn already the basic lessons from those. Okay, so it's not even in full screen mode. Okay, never mind. I'm trying to be kind of easy and only slowly go into more mathematical statements. I mean, I said it already. Okay, we have this wave function. In the mathematical description, states, a quantum system is described by Hilbert space. You need to know somehow what is the Hilbert space of the quantum system. That usually already requires some work. The states are unit vectors in this Hilbert space, or rays. And we have to make this observation we make with so-called observables. So in the old school textbook quantum mechanics, these are just Hermitian matrices, and their eigenvalues and eigenvectors, they correspond to how the observation is done. And so one of the very first observations you have to make when you start discussing this problem is, well, can you actually learn what X is? And so the ideal case is, well, you can learn it perfectly only if there is a single observable. Obviously, we have one shot. We have to make one observable. If there's a single observable, and these states are different eigenstates of that observable, and that means they must be orthogonal because it's a Hermitian observable. And so if not, then we cannot distinguish them. But okay, this is nothing particularly mysterious. This is like having a probabilistic signal with overlapping supports. Okay, again, so those things you cannot distinguish. So there is some kind of element of preparation and detection irreversibility, but it's somehow built into the statistics. Oh yeah, this is a caveat. Of course, it's a statistical theory, and when you talk to people from the old quantum mechanics, they would say, oh, well, but okay, there is no such thing as a single quantum system. I mean, what I do is I prepare a gazillion atoms, and then I make a measurement, and then I will not just learn the statistics. I can learn any property I want. And of course, that's also contained in my model here, but we have to say explicitly how many instances of this system, how many copies of that state I have. And the very elementary but important insight is there is always a measurement, there is always an observable that for my two states will produce different statistics. So if I just take enough samples, I will be able to tell them apart. But this is not the setting I want to discuss for most of the talk. I want to look more in this communication setting where there is a single secret, a single shot, and we have to make the best of it. Okay, so here's a bit of outline. I mean, this may be very optimistic, and I may have to sacrifice something there at the end. So let's just go into a more of a concrete or mathematical description of the discrimination problem. So in general, okay, so I said we have this Hilbert space. In general, we have different states, as I said, one of two, and they are not just these unit vectors in Hilbert space, but the correct and general description is as density matrices. So these are the analogs of probability densities, discrete probability densities. Okay, and so these are, for all of what I'm talking about, you can think of these as positive semi-definite matrices over the complex field with trace 1. And so that is a strict generalization of probability distributions, because if you restrict your attention to diagonal matrices, then you get a list of positive numbers that add up to 1. Yeah, so that's a discrete probability distribution. So it helps us usually to think of this as a density, even though there is no associated sample space automatically, right? So as I said, the measurement, we have to make it up, and this goes as follows. Sorry. We have I wanted to link back to the cartoon I had before. We could, for example, have projectors onto one-dimensional spaces. These are called pure states, but in general, you have convex combinations of those. Okay, as I said, to distinguish, we need to make measurements, and so this is also well understood mathematically how to describe those things. These are just bunches of or families of positive semi-definite matrices adding up to the identity. So the probabilistic analog would be a partition of unity. It's a set of non-negative test functions that add up to 1. For example, they might be mutually orthogonal projections. So of course, we have a simple problem with 2 hypotheses. Obviously, I need a measurement with 2 outcomes. And so these 2 outcomes, they correspond to 2 operators. And so the one piece of quantum physics I'm going to teach you today, if you didn't know it already, well, I suspect that lots of you do know it already, is the probabilistic rule, the Born rule, after Max Born, who got this right in the early days of quantum mechanics. So to characterize the probability, if the state preparation is rho x, and the measurement is described by these 2 operators, preparation x and outcome y, given preparation x, the outcome y has this probability form. And so all the axioms about states and measurements, they're made in such a way that this is always guaranteed to be a probability distribution. So non-negative numbers adding up to 1 when you sum over y here. Okay, so to have a concrete goal, we want to maximize our success probability, right? In the cartoon, where was I? Here in my cartoon, Flash Gordon and Dr. Sarkov, they're preparing row 0 or row 1. And here, Marie Curie and her daughter, they're trying to figure out which one it is. So, and let's be simple. There is a probability, somehow these 2, they know, okay, with probability p, it's going to be row 0, with probability 1 minus p, it's row 1. And so this is our objective function. So as you notice, I have no hesitation about the mathematics, right? So when I said before, quantum mechanics is also mysterious, it's not the mathematical formalism. I mean, this is something that people figured out, Heisenberg, von Neumann, in the 20s and 30s already. I mean, we have 80, 90 years of experience with the maths. So there's barely any kind of deep mystery. I mean, of course, there are technical problems, but the stuff I'm discussing here, this is very straightforward, and von Neumann could have written this. The mysteries are always to do with the interpretation, right, or with the implications. It's to do with how I want to talk about it. I will try to avoid this here because now I have the math. I can just talk about it like a normal person. So let's do a bit of math on this slide. We want to maximize this. That's the usual problem of Bayesian inference. So let's get rid of one of the variables because m0 and m1, they add up to 1, so I can substitute here. Then I can simplify a little bit, and I get this one. Then I can rewrite it a little bit, and I get this one here. So the success probability is 1/2 plus 1/2 times some crazy trace. This is not a probability because this is a difference of 2 density operators, and this is a difference of 2 measurement operators. But we know what this maximum is because this is something with eigenvalues between -1 and 1. And so this maximum here, this is something known as the trace norm, or non-commutative 1 norm. I'm not claiming that this is a closed formula, but it has at least, it connects it with some other interesting properties of matrices. These non-commutative p norms, they are very natural objects. And okay, I'm going to tell you how to calculate it. So this kind of consideration that goes back to the 60s. Carl Helstrom wrote a paper and later a book about quantum detection. And of course, also Alexander Holevo worked on these problems. This is all elementary here, mathematically speaking. So the trace norm is this one. It's just a trace of the absolute value of A. What's the absolute value of an operator? Well, it's the operator that has the same eigenbasis, and we're talking about Hermitians, but the absolute values of the the eigenvectors. It is the same eigenvectors, but it's the absolute values of the eigenvalues. So this requires that you know the eigenvalues to calculate. This is why I'm saying it's not really explicit, it's not really a closed formula, but it gives us a handle because it has this norm. So for example, for pure states, and in the case which I will discuss mostly of equal probabilities, we can calculate this in terms of just the inner product of these two states. So this is very nice that there is kind of, this is the easy part. We can even describe the optimal measurement, which again goes back to Helstrom. Look at this difference. This is a difference of two densities, so there's a positive and a negative part. Just look at the eigenprojection of all the positive parts. And this is one of the two operators, and the other one is the orthogonal complement. And consistently check, when is this probability 1? Well, then this guy has to be 1, and this happens if and only if the two states have orthogonal supports in Hilbert space. So if the product of them is 0, that's the same. Product of them is 0. Well, okay, let's talk about the asymptotic version again. Very briefly only, just so that I can put some references. Of course, we might contemplate that you have access to somehow many instances of this state preparation. So what that means is that you have a state rho tensor power n. Why? Because the density of the states if I want n copies, I need to describe somehow the Hilbert space of the n copies, and that's first of all the Hilbert space tensor product. And then the densities are, in the simplest case, just tensor powers. And so in this case, the success probability goes to 1 exponentially, and this number here has been figured out a few years ago. This is known as the quantum version of the Chernoff coefficient. It's just the minimum of these traces. So this is related to, this is up to the log, this is a relative entropy, actually. Or there are also, so this is the case of my two hypotheses with probability equal to a half, p equal to 1/2. There is, of course, also, just like in ordinary hypothesis testing, the asymmetric version, so that we look separately at the error probability of first and of second kind. I hope I got it right. I'm sorry, this was late night that I added this slide. So one of them is just supposed to be bounded or going to 0, and the other one goes to 0 exponentially, and then the exponent is this one here, which is the quantum version of the usual Kullback-Leiber divergence or relative entropy. There are plenty of names for this. And so here I was running out of space for the reference. I put just the names of the main protagonists who did this in the quantum case. And okay, I don't want to pass this point without mentioning that indeed, just like in the Shannon theory, especially this asymmetric hypothesis testing has a lot of implications in communication theory. So we get proofs of direct coding theorems, we get converses, we get finite block length analysis from, not using directly the Umegaki relative entropy, but relatives of that. So, yeah. I need to find a way of getting back to my original path. So let's, but that was just a nod to a bit of literature. So I was always sure that I wouldn't have enough time to go into any kind of actual discussion of quantum information theory. So my original problem, we have the maximum success probability, and I even told you what the measurement is. And so what I'm going to be interested in for the rest of the talk is, so what happens if this measurement somehow is not accessible? For some reason, I call it, we cannot perform the optimal measurement. So I'm speaking here on behalf of the Curies. It might be some crazy, highly nonlinear observable of position momentum. This is not easy to do. Or it might require that you create a probe. It has to be prepared in a superposition of, for example, 0 and 1 particles, which is fine if it's a photon, but it's a problem with the Higgs boson. I mean, we know that it exists, but we are not able to control its dynamics. So there are, and this is something I believe that is entirely quantum mechanical, because we have to somehow first design, we have to provide the sample ourselves. Right? In the classical statistics, part of the description is the sample. You get Y. That's it. Whereas here, I give you the state. And so the decision rule is somehow folded into the other problem of obtaining the sample in the first place. I mean, I assume that once we have the sample, we have the outcome here, we can make a rational choice based on ordinary statistical theory. But we have to make this measurement. And making one measurement precludes making other measurements because they're not compatible in quantum mechanics. So the rest of the talk, as I said, is what happens. We will look at specific restrictions on those measurements. In this case, of course, this equality sign turns into an inequality, so we get something strictly smaller, and something will have to replace this expression here. And okay, so at a certain point, I will just silently assume that p is equal to 1/2 because, well, some expressions, they just turn out to be simpler, even though in the beginning, as you see at the beginning, I tried to be more general, but actually, it's, in the end, I was foiled by my attempt to be a little bit more intelligible. So, what is this? Oh, sorry, this is already jumping ahead. I hope this was more or less okay so far. This is, I mean, obviously I started a little bit philosophical. Now I will do more information theory. I want to discuss, as I wrote here, these two acronyms. These are two codes for specific restrictions that came up more or less naturally in various discussions. The first one more than 20 years ago, the other one is a bit more recent. And okay, let's see what we can do with that. So this, the first restriction, we call it LOCC, that is an acronym for local operations in classical communication. So the setting is the following. The Hilbert space is itself a tensor product. Why? Because it describes the joint system of two players that are maybe far apart. So Alice and Bob, they have their own quantum systems, but the joint system must be the tensor product. And without capability of quantum communication between them, the only thing they can do are sequences of doing something locally in their labs, quantum mechanical operation, which basically means measure part of your system and tell the other party your outcome, and then the other party decides on what to do next in a similar way. And so one thing that you have to appreciate is this gives only a very small subset of all the available measurements on the joint system. So, and I drew another cartoon. I need more scientists, obviously, so Marie Curie has had a day. So we need these two. And so what you see from outside is just these messages passing back and forth. And at the end of the day, one of them will output the guess for the X here. Right? It's the same thing. So in between, they locally made some measurements. So each system maybe is composed of many individual particles, and each round of the protocol will require measuring some part of that system in the same way as I wrote it before. And so the starting point of this discussion is a wonderful result by Walgate from 2000, that if the two states are pure, then we can always distinguish them perfectly. Sorry, not perfectly well if they are orthogonal, but if they are not orthogonal, we can always distinguish them by this kind of procedure, as if the two were able to make the optimal Helstrom measurement. On the other hand, we can always distinguish two states if they are different in some way by just obtaining local information. This is a peculiarity of quantum mechanics. So I think in the official jargon, this is called local tomography principle. If you just make the right kind of measurement locally, pool the results, you get different statistics. And from different statistics, you get some kind of small signal of what the X might be. And the concrete lower bound is like this. So I remind you here, I'm talking about equally likely hypotheses. So the guessing probability is for sure always at least 1/2, and then you get some small advantage from using the statistics. And the particular measurement that you can discuss is, for example, each of them just chooses a random basis in the corresponding Hilbert spaces, makes the corresponding measurement, and they exchange the outcomes. So yeah, the lower bound is in terms of the 2 norm. This is, again, a non-commutative version of the 2 norm. This looks much easier than the 1 norm, and much more like a norm, maybe. And so in terms of the trace norm, which is the one that we'll know from the Helstrom bound, it's like this. So as you see, there are these kind of weird numerical factors. I will tend to ignore them. This is just a constant. What is not a constant is the dimension, because that's something that is a property of the system. If the dimension is large, this can be very, very small. So it looks like I can push the success probability very close to 1/2. And indeed, this kind of measurement is very bad in general. And the beautiful thing is, well, okay. The beautiful thing is there is an example where this sort of scaling is optimal up to a constant. And this was also discovered similar time ago. The example is the following. This comes from the representation theory of the unitary group. Both systems of Alice and Bob are d-dimensional. And rho 0 and rho 1 are the densities corresponding to the fully symmetric and the fully antisymmetric subspace. These are the 2 irreps of the representation of the unitary group that acts as U tensor U, that acts in the same way on both of the systems. So these are 2 very beautiful and highly symmetric states. They are orthogonal to each other, so according to Helstrom, they are perfectly distinguishable, but this is a measurement that you have no access to in LOCC, and in fact, it's so bad that the optimal success probability is 1/2 plus this order 1/d. And you might say, well, okay, this is maybe very fast. Turns out that these 2 states, of course, they are correlated. I mean, they don't encode the information locally. In fact, locally, each of the 2 states, they look exactly the same. So it's in the correlations that this hidden information is residing. In fact, these authors, they call this quantum data hiding. And in fact, it turns out even one of them is even quantum correlated. So it's an entangled state. It's not just a mixture of local preparations. So in the early days, some authors would argue, well, okay, maybe there's something genuinely quantum going on here because one of the 2 states is quantum. But it turns out that, again, almost in the same year, some other authors could find, so this is from Eggeling and Werner's paper, could find 2 examples where both of the states are unentangled. They are almost perfectly distinguishable, so the trace distance is arbitrarily close to 2, and the LOCC distinguishability nevertheless is very close to 1/2. Yeah, so maybe I shouldn't dwell on this too much, because ultimately this was more of a red herring. I apologize. Maybe I should have just canceled this slide. Okay, yeah, since I discussed the many copy, the Chernoff bound setting, it's also kind of entertaining to look at this here. So what happens if we have many copies of the state available? And, well, obviously in the Chernoff setting, sometimes the single copy distinguishability may not be that great, but then asymptotically it can be almost perfect. So it turns out these 2 states, they are actually also very good to stump any kind of asymptotic attempt, because the scaling is similarly very bad. So if the dimension is large, this is close to 1. And so, of course, the success probability goes to 1 exponentially, but very slowly, because we can make the dimension very large. Okay, so I want to kind of take a step back from this. So this was a bit of history of these early days, the restriction of local operations and, well, classical communication. So the abstract model is, which I discussed in the paper with Will Matthews and Stefan Ivena, you have some kind of restriction on your measurements. I have to look at the time, I guess. You have some kind of restriction on your measurements, and I just gives this a name, a class aim of measurements. And then we would like to do some sort of an optimization over all the possible measurements you can make from this class. And then, okay, based on the measurement result, you make your optimal choice of inferring X from Y, yes? And so the form of the optimal success probability is always like this. It has to be, because you can always guess with probability 1/2 which one it is. And so you ought to obtain some advantage. There must be a plus something. And this plus something, this green part, this turns out to be a norm. Actually, it's a semi-norm in general, but I will assume that the class of measurements is rich enough so that it can always distinguish at least partially any two different states. It's not a very important restriction. And so this is a very roundabout way of defining the trace norm according to the Helstrom theorem, if M is the set of all measurements, but in general it's much smaller, as we have seen. Yeah, so these results from the previous slides, this kind of thing, I can phrase it as saying, aha, the difference of rho 0 and rho 1 in the trace norm is 2, but in the LOCC norm, it's order 1/d. Right? So it turns into a functional analysis problem of comparing the properties of different norms. And so the whole investigation of LOCC is understanding what the norm is, the unit ball of this. How does it compare with the trace norm or with other norms? Before I leave this LOCC, just one word. Local operation, classical communication, that doesn't even make sense as a restriction in an ordinary statistical setting. Because what could that possibly mean? I mean, you give a sample to Alice, you give another sample to Bob, and now they are allowed to look at the sample, okay, that's perfectly possible, and exchange notes about them. And so why should that be a restriction? Because obviously they could just tell each other what their observation is. Yeah, so LOCC, as I phrased it here, as a restriction, it's something quantum mechanical. It comes from the fact that by looking at the system, you make a choice already that you extract some kind of information, but that will preclude getting others. And maybe your friend, Alice or Bob, later tells you some information, and then you regret it that you made the measurement before, but then it's too late. And so these kind of things, they don't appear in ordinary statistics. What you can do there is, of course, you can, for example, limit the amount of communication between the parties. And then you will see similar things. They will not be able to make the ideal test, but something slightly worse. Okay, so here are the distinguishability norms. Yeah, so for example, what we looked at in this paper was M consists of a single measurement, a measurement rich enough to give you statistics to distinguish any two states with some probability. And then the norm has this kind of deceptively simple explicit form. So for example, if the measurement is somehow has projections made up that are somehow sufficiently uniformly distributed in the Hilbert space, then this norm is essentially equivalent to the Hilbert-Schmidt norm, to the 2 norm, which is kind of unexpected. It's a beautiful result that goes back to Ambinis and Emerson. So this is what you get when you have just one measurement. If you say, okay, like I don't want to deal with all of this stuff of optimizing my measurement, trying to think about how to measure this and that. It gives you some distinguishability, but it's in general very far away from the Helstrom, which is the 1 norm here. And so data hiding, contrary to the paper of Terhal et al., data hiding is about having two states that are in trace norm almost perfectly distinguishable, so I need that this goes to 2, but in the M norm, they should be very close. Yeah, so that's kind of what this data hiding amounts to. And of course, you can ask the same question about the Chernoff coefficient. So when you have many copies of rho and rho 1, you can try to bound what this Chernoff coefficient under the restriction is. And so it turns out, for example, for the result I showed for the symmetric and antisymmetric states, this can be realized for LOCC. And again, before I move on, I just want to make a nod towards applications that these norms have found in not just in quantum statistics, but in information theoretical context. And maybe the strongest one is from a recent paper by Brandau and Harrow. They prove so-called finite Definetti theorems. So Definetti theorems, they approximate, they are statements about approximation of n-fold exchangeable states on an alphabet or on a quantum system, comparing those with tensor products and their convex combinations. And so the ideal thing that you would like to do is you would like to make approximations in the trace norm, because this gives you control on the statistics. But what the best results that we have for this are with respect to some of those LOCC norms. So I mean, they're obviously equivalent for any finite system, but well, that's kind of the state of the art. Okay, I think I have time to do a little bit more physics. So this is the other acronym, GOCC. This is not, I mean, I didn't invent this name, sorry. Sorry, I wanted to start with Sasaki and Takeoka. So the question I want to start with is one that was formulated by two colleagues, Sasaki and Takeoka. How well can you distinguish two states of a single bosonic mode? So this would be a kind of quantum harmonic oscillator, the simplest quantum optical system. And coherent states are given by complex numbers. So we're talking about laser, but the weak sort of laser light that we have in the quantum communications labs. The mathematical description is basically that. So it's about the harmonic oscillator. This works in quantum mechanics just like in classical. You need a position and momentum variable. You have to write a Hamiltonian, and then that determines the dynamical equation. So the Hamiltonian is basically x squared plus p squared if I set all masses and other units equal to 1. X and p are position and momentum, but in quantum mechanics they satisfy the famous commutation relation. And okay, so the Hamiltonian up to this constant 1/2 is this guy here. This is A dagger A, the number operator, where A is the annihilation operator, so-called annihilation operator. And this annihilation operator, this one, you need to define what the coherent states are. They're exactly the Eigen States of this guy. So this is an unbounded operator. It's not Hermitian. It turns out its eigen values are precisely all complex numbers. Each of them appears exactly once, and the eigenvectors are these coherent states. And these are beautiful states. They are kind of the almost classical states. They are the states that have x and p not precisely defined, but they have the kind of the expectation value coming from the real and from the imaginary part of alpha. So kind of this I here is kind of has the same origin as Y in electromagnetic communication or electromagnetism. We have complex numbers because it's just a convenience to integrate the two field numbers into one complex number. So the alpha has a real and an imaginary part, and these are precisely the expectation values of x and p, and they have some uncertainties, so they have delta x squared and delta p squared, and they are the smallest they can be, according to, consistent with the laws of quantum mechanics. And so in my units, they are 1/2. So these are kind of, turns out these are the states that are the easiest ones to produce in a laser, for example. This is essentially a coherent state with a very high approximation of accuracy. So yeah, Takeoka and Sasaki, they asked, okay, so how well can we distinguish two such states? Because these are the things that also will appear in ordinary quantum communication scenarios, in the theory, of course. In the practice, everything is much messier. We will prepare coherent states. And so we can try to work out the Helstrom bound. Well, these are two pure states, so we just need to compute the inner product. It turns out it's this one. It's this exponential of minus alpha squared. What Takeoka and Sasaki proved a few years ago is the optimal measurement with, well, what we would call in the jargon linear operations, in the most general linear operations. So this would be, in operation terms, you can have free ancillary modes in vacuum. You have free Gaussian operations, and you can do iterative measurements on the modes and then feed forward the result. So this is like the LOCC, that you make only a partial measurement on the system, and based on the result, you decide what to do next. So there's an element of mixing obtaining the measurement result, that you don't do all in one go. You make a partial measurement. And then there is a classical computation part. So maybe the CC is something like classical computation. And so the optimal distinguishability according to the GOCC is slightly different. It's not this exponential function, it's an error function. So it's a tail of a Gaussian. And there's a very simple way of seeing that, which I don't know if I should go into this now. Well, I think I have just 2 slides about this. So if you know okay, now this is, if you heard about Vigna functions, that's very nice. So the Vigna function is a way of representing the state in the phase space, and it's particularly nice for these coherent states because they are just little Gaussian packets centered at alpha, well, times a unit because of the way I chose the observables, and with standard deviations like this here. But so in general, you have this Vigna function that is not a probability distribution, but a quasi-probability distribution for every quantum state. So that it can be negative, but will always integrate to 1. And it has the nice thing that it also assigns a function on phase space to the measurement operators. And for the Gaussian measurement operators, and more generally for GOCC, these correspond also to non-negative Vigna functions. So then it looks like we have probability distributions and ordinary test functions that add up to 1. And this implies that the GOCC distinguishability of any 2 states is bounded by the L1 norm difference of the corresponding Vigna functions. It's just a bound. The right-hand side might even diverge. It could be infinite. But for the case of the 2 coherent states, this is optimal. So this is an equality. And the optimal strategy is measure x coordinate. X is an observable in quantum mechanics. Measure it and decide whether it's positive or negative. Because one of the guys is a Gaussian centered at plus alpha and the other one minus alpha. And so, yeah, turns out, okay, these two things, they are just a little bit different. Okay. They are different, but not so much. For example, the largest gap appears so alpha, this is something, this alpha, you should think of this as the square root of the mean photon number in my units. So like if at alpha equal 1, we have roughly 1, I mean, on average, we have 1 photon in the thing. The largest gap appears somewhere down here, but it's still very small, between the 2 norms, right? So it's not, okay, there's a bit of a difference, but it's not like data hiding as defined by Terhal et al. So the question that you should have immediately is, well, can I make big gaps? Is there hiding? And the answer is yes. I wouldn't be standing here and telling you this story if there wasn't. But you have to go to multimodes. And for multimodes, you can make 2 states that are each of them mixed states. They're mixtures of coherent states, so they're still relatively easy to make. And under the restriction, they are exponentially close in the number of modes, but they are almost orthogonal in general. In fact, the beautiful thing is one of them could even be a thermal state of the field. So the way these states are defined is actually the background is a thermal state of all of those modes with a certain intensity, with a kind of certain virtual temperature. The other one is just an approximation of this mixture of coherent states. And so it turns out, so the argument using these Vigna functions again is strong enough to even give you a bound on the Chernoff coefficient. I don't know what the number is precisely, but it's a bound. It's somehow to say, okay, you just have to make n large enough, and then this can be small, this can be close to 2, etc. And so, to complete the comparison of the 2 norms, we should do something also from the other side. We should say, we should come up with some kind of strategy that gives us at least a guarantee of distinguishing 2 states, let's say 2 states that are close to being trace distance 2. Can I give a guarantee that with under the restriction I can still distinguish them so and so well? Like the very first thing I showed for the LOCC, that you do just this very simple fixed measurement, and then you just look at the statistics. So this ought to be possible, even though my theory of this is still very incomplete, but it's probably also because I'm I'm not the greatest expert in quantum optics. For example, some measurement that is very popular and very commonly used both in theory and practice is so-called heterodyne detection. So the collection of all the projections onto the coherent state, that's a measurement with a continuum of outcomes. If you integrate all of this with the correct normalization over the complex plane, you get the identity. And this is, sorry for the jargon, tomographically complete, meaning that if you look at the statistics that you obtain from this, for two different states, the two statistics will be different. So there must be some kind of small gap. There must be some small number of distinguishability. So the question is, how well is it? I need to put a number to this. And so far, I don't have very complete results on this. So, for example, just for a sample, I want to show you this here from some ongoing work with KK Savapati. We can prove a lower bound on the distinguishability with a slightly larger class of all measurements with positive Vigna functions themselves. So these are like Gaussian, but it's really a larger class. And so you have a lower bound in terms of the 2 norm and the number of modes. And so if you put some additional numbers into it, for example, like in the construction, we have a finite energy per mode, or a total finite energy, or well, maybe it's better I should talk about photon number in this context, then you get a lower bound like this. There's this delta here, this can be some constant. This is exponential in the number of modes. So what it tells you is if you have constant energy per mode, you need a large number of modes to make this small. So in a certain sense, the construction is not so bad because, I mean, the fact that we have to go to this multi-mode is somehow inherent in the formalism. If you don't do this, you need enormous energy. And yeah, so I thought I would put this here, but for a while I thought I can prove this even for the heterodyne detection, but so far I haven't been able to do this. And so yeah, maybe this is the moment to skip ahead. So I wanted to come back to this data hiding. There is a beautiful kind of other direction that goes beyond two hypotheses. You want to ask the question, so how many bits can I hide? I mean, of course we can hide one, that is the original paper, but if I have a d times d dimensional system or n qubit and n qubit system, how many bits can I insert in this? So also that is kind of a fruitful direction. It's much more like communication theory or cryptography. And so, okay, the result is this one here. So if you have two d-dimensional quantum system, the amount of information is log d. And maybe I should, yeah, so what I want to convey here is yet another kind of connection to a sort of different sort of statistics, and that's secret sharing, which is also a kind of in fact, it's kind of maybe this is the best classical analog of LOCC. You distribute information into correlations between different parts. It doesn't reside in the individual parts, so it's hidden from people who have only access to certain parts. But if they can look at the whole thing, then they see the correlation, and then they can work out what the information is. And you can do this not just to encode a single bit, but you can encrypt a large number of messages. And so one of the most fundamental bounds about these secret sharing schemes is actually the encryption is the encryption bound of Shannon. So this, in this setting, it says in any tight secret sharing scheme, so in tight in the sense of Shamir and Blakely, each relevant share must have at least the size of the secret message. So this is reminiscent and actually equivalent to the statement in any perfect cipher, the key must be as large as the message. And it's attained for threshold schemes. So it turns out, and without me showing this now, quantum data hiding with many parties and restricted to LOCC, it has a very similar structure, and most beautifully, it has the same kind of bound. The limit for how much information you can encrypt is the size of the smallest share. So this is all jargon, blah, blah, blah. Why do I have this? Do I have time for some discussion, or do you want me to close? Yeah, so this I said already about the data hiding. Unfortunately, I didn't have time to show you a beautiful thing defined by Mark Wilde and his group, the data hiding capacity of an agent who wants to prepare hiding states. Let's forget about this. So what I want to talk about is the reason why this is interesting in quantum information theory, maybe ultimately. Every such restriction, it somehow, you studied enough, or rather, right at the start, you learn that, well, it's a restriction, obviously, it prevents you from doing certain things optimally, but it also points to a resource. It points to something that allows you to overcome it. So in the case of LOCC, the reason why LOCC is so important in the theory of quantum information is because it's somehow the operational set of operations that defines entanglement as a resource. Entanglement is the one thing, if you have enough of it, then LOCC becomes the same as all operations. And entanglement is quantified as monotones with respect to the LOCC operation. So one of the questions I have is, for this GOCC, what's the resource theory? What is the resource? How can we quantify it? So this seems to be very relevant for the physics of quantum information, where a lot of experiments or implementations are done in quantum optics. And yeah, that seems to be the end. Thank you very much.
Yes, thank you very much. And we have time for 2 questions. Are there any or comments? Seems not. Oh, yes.
Yes.
So you alluded to this earlier, but can you comment on how close you are to being able to experiment and validate some of these methods in practice?
Okay. Repeat the question.
Okay,
please.
so the question was, obviously I presented the theory and the mathematics. How close is the experimental or physical reality to this? As far as I know, nobody has implemented the data hiding scheme. I mean, because to do that, you would need a kind of a largish number of qubits. I mean, I would like to see the Gaussian part implemented, because that's just simple linear optics. But I haven't found an experimentalist yet who wants to do it. But I think the technology is there in principle, and it can provide a beautiful benchmark to quantum opticians how well they can do certain things.
Okay, thank you.